Is that okay?
Mm-hmm.
Okay, so yeah, my name is Matt Zabka, and thanks for inviting me, Eric. And, my goal is to give you a really brief introduction to a field that I'm somewhat involved with, called topological data analysis. So I don't want to get too technical. What I want to do first is just give you a lot of pretty pictures, give you some intuition as to what topology and algebraic topology are. And then we'll talk about how those tools are used in data analysis. And then I have a bunch of, applications for you to play with, and a bunch of problems for you to solve. And if we have time, we'll get to what's called multi-parameter persistence. But that's the outline. So what's algebraic topology? Well, first, before you talk about algebraic topology, you should know what topology is. Topology is just a study of continuous functions. But that's useful in extracting global qualitative features from some complicated geometric structure. What algebraic topology does, it assigns algebraic descriptors to topological objects. So topological questions can involve things like connected components. How many loops are there in a manifold or space? How many voids are there, for example? In two topological spaces in topology, we say that they're the same if one can be continuously deformed into the other space. So here's a question for you. I have 4 manifolds, A, B, C, and D. And the question is, which of these can be continuously molded into each other? And if you're not happy with the notion of continuity, you can think of it as, well, you're not allowed to tear or anything. So the important thing is that you have to be able to mold one thing into the other thing, and you have to be able to mold it back to how it started. So are any of these the same in the lens of topology?
A and D.
Yeah, A and D. That's right. A and D are the same. And why are they the same? What's the easiest way maybe to see that they're the same?
Make about circles.
That's the right thing, actually. That is exactly what I would say. I would say, hey, look, there's one loop right here in the A. And there's one loop right here in the D, right? So if I wanted to deform the B into the A, how could I do that? Well, what I would need to do to the B, the very first thing I would do is I need to change these 2 loops into a single loop. So what would I need to do? I need to rip the middle part of the B up. Well, I'm not allowed to do that in topology because that's not continuous. So the only 2 letters here, and maybe if you ever take a topology course, which would be, I recommend, it's a lot of fun, the first assignment that your professor would assign is to tell him which letters of the alphabet are the same in algebraic topology. So can anyone think of any other letters that are equivalent to A and D in algebraic topology? P, O, Q. What about C? What is C the same as?
I, L.
Well, I. That's a good question. It depends on how you write it. I. I'm serious. If you write an I like this, yeah, that's the same as a C to me as a topologist. But if you write an I like this, then they're very different. Why are they different? Because there's 2 pieces. And look what it says up here. It says topology. Well, it says it up there somewhere. Connected components. There are 2 components in this I, whereas there's only 1 component in that C. So those are the types of things that we want to be looking at when we're talking about topology. Great. So what does algebraic topology do? So that's what topology is. So what is algebraic topology? Well, let me ask you a question. Is this space, so this is just like the letter O, there's a hole in the middle here, and this space where it's the disk, are those 2 the same? Can you continuously change this into this one and this one and this one without ripping it? And the answer is no, you can't. But how can you prove that? I mean, can you find a continuous function that goes from here to here and then an inverse continuous function that goes from here to here? Can you do that? And the answer is no. But how do you know that you can't? It's a really, really hard problem that stumped a lot of smart people for a very long time. They said, well, I don't think these are the same. But just because you can't come up with a function doesn't mean it doesn't exist. And so the only way that people could come up with to solve this problem is they said, well, you know what, this is a topological space, but I'm going to assign this some algebraic structure. And what I'm going to do is I'm going to look at a path in this space. In this path, I'm going to count the number of times that it goes around. Starting here, goes around a bunch of times, stops here. Maybe if it goes around n times, I'll assign that the number n, right? And so the question is, well, what algebraic structure is assigned to this? It's called a winding number. What algebraic structure is assigned to it? Well, I can go around this way as many times as I want, but I can also go in the reverse direction as many times as I want. So the algebraic structure assigned to this guy is the integers, right? What algebraic structure is assigned to this guy? Well, it doesn't matter if you try to go around like this. What can you do with that path? Well, I can shrink this path continuously just to the starting point, because it's a disk. I can just, like pretend it's made out of Play-Doh. I can just smudge it down into nothing, right? So actually, all of the paths in this space are the exact same thing. But if you go around twice in this space, well, you can't continuously deform that going around twice into going around once. So what's the algebraic structure that's assigned to this? Well, it's the identity group, if that means anything to you. But it's just a group with a single element. And that is how people show that these two spaces are different. It's because it's not, you can't just stay in topology. You have to translate it into the language of algebra and then say, hey, the algebraic structure associated with this topological space and the algebraic structure topology does is it takes a topological space and assigns to it some algebraic structure, like a group, ring field, vector space, something like that. Today what we're going to do is we're going to be working over the field F2. If you don't know what that is, I mean, you've all taken a course in linear algebra, right? Everyone's taken linear algebra at some point. And then you talked about a vector space over a field, right? And then maybe the instructor never brought it up again. But fields are rich algebraic structures. I mean, lots of things are fields. This is F2. And it's just, I mean, what do you need to be able to do in a field? You need to be able to add things and multiply things, right? So 0 times anything is 0. 1 times anything is that thing. The only weird thing that happens here is what's 1 plus 1? 0. That's it. So that's the field we're interested in here, is that basically something's either off or it's on. And that's it. Okay? And then again, the important thing is that if two spaces are the same, like if you took that A and that D, and you assigned them some algebraic structure, those algebraic structures have to be the same. On the other hand, if you have two spaces that are different, then their algebraic structures need to be different. And that's how we tell whether two things are different. Any questions so far? You kind of get an idea of what topology is and what we're doing to go from topology to algebraic topology? Great. So topological data analysis uses topology to summarize and study the shape of data. And here are some applications that I just took out of a book. But this is what people are using. This relatively new field, I think the first big papers came out in 2007 using this. But I don't know, the things I'm familiar with are the fMRI data and the example of finding a new type of breast cancer. Those are two famous examples. But a more recent example, I don't know if you guys have heard of like the Blue Brain project, but people are trying to study the way that different neurons communicate with each other using these methods. So lots of different applications to how topology can be used in data analysis. So there are two main tools that are used in topological data analysis. The first one we're going to talk about today is called persistent homology. Homology is one of the algebraic structures that can be assigned to a topological space. So I'll give a brief introduction of what homology is. Mapper is a dimension reduction tool, and we're not going to talk about it all today. We invite you back if you want to learn more about it. So a simplicial complex is a combinatorial object, and it's basically a graph, but a higher dimensional graph, I guess. Each simplicial complex is built out of simplices of varying dimensions, so I just stole this from Wikipedia. But remember what we're trying to do. So this is a topological space. Just like this is a topological space, this is a topological space. A simplicial complex is a topological space. And from that, we want to use algebra to assign certain numbers to this topological space, or certain structures to this topological space. So if you look at this topological space, so that's a Greek letter beta. I gave this talk before and I just started saying the word Betty, because in algebraic topology we call these Betty numbers. So we say Betty 0, Betty 1, and Betty 2. Yes, it's the letter beta, but these things are named after someone whose name is Betty. So What is Betty 0? It's the number of connected components. So how many connected components do we have here? You can say it.
3.
3, that's correct. Betty 1, how many holes do you see? Now, when you say hole, I'm talking about a one-dimensional hole, something you can stick your arm through.
1.
Yeah, 1, right? Where is the one-dimensional hole?
The bottom.
Yeah, it's right here, right? And how many voids are there? So when I say a void, if you think of a sphere like this, right? Like a hollow sphere, that's a void, right? So how many voids can you see? It's not really fair for me to ask this, but how many do you think there are?
1.
Yeah, 1. It's 1 as long as what? I mean, it's kind of, you can't tell from this picture, but what? As long as this isn't filled in, right? If this is a solid tetrahedron, then there are no voids. But I mean for this to be a hollow tetrahedron. Okay? So that's correct. We have 3 connected components, 1 hole, and 1 void in here. And I think you can see that, I mean, if you could keep going up, if we could see more than 3 dimensions, you could continue this process. Great, so what is homology? This is maybe the most technical slide that I'm going to give you today. In degree K, so every degree 0, degree 1, degree 2, has a homology group assigned to a topological space. And what it is, it's the K cycles modulo the K boundaries. What does that mean? Well, what I've done right here is I've drawn 2 different cycles. Right? Here's a cycle, here's a blue cycle, and here's a different blue cycle. And what I mean when I say modulo the boundaries, if you remember from your group theory, right? If you have a group and you mod out a normal subgroup, it's kind of like you're collapsing your group to a smaller group a little bit. That's what's happening here. So I have a cycle right here, but every simplex that touches this cycle is part of the boundary of that cycle. So what I'm doing here is I'm taking this cycle, but I'm going to collapse away the boundary. So what does this first cycle become if I collapse away the boundary?
Just a boundary.
Yeah, it just becomes a point, right? So if I say, hey, I've got a cycle, but remove the boundary. Well, if you remove the boundary, then that cycle's just going to get plopped down to a point. What about this cycle, though? What happens to this cycle if you modulo the boundary, if you get rid of the boundary? All that's going to happen is you're going to take this part right here and you're going to collapse it. What are you still going to have? You're still going to have a loop in there, right? So this cycle in homology is not important. Homology wouldn't see this cycle at all because the boundary modulos it out to a point. Whereas this cycle here would be important. So that is how homology works. And then we say that Betty K is the rank of the homology in degree K. So this cycle right here is a generator for, you can either say the group or for the vector space in dimension, this would be dimension 1. Right? This is a one-dimensional cycle. So that's a loop. Okay? So in this case, we'd say that Betty 1 is equal to 1 because this cycle right here is the generator of the homology group. So here's the general pipeline of how topological data analysis works. We start with data. From those data, we create a topological space, which is going to be a simplicial complex. From the simplicial complex, remember from topology, we're going to go to a vector space, an algebraic object. And from that algebraic object, we can then perform statistics. Okay? I hope to get through steps 1 and 2 today. And then you can do 3. So if you have a data cloud, how do we create a topological space from those data? That's the first step. So here, we start off with a data cloud, and we have a point cloud, which is either, you can say it is a finite metric space, or it's in a finite metric space. And what we're going to do is we're going to add a parameter, and what that parameter is going to do is it's going to create a radius, or a circle of radius r, that's the parameter, around every point. And then we have an algorithm for creating a simplicial complex. We say that if 2 circles intersect, we're going to create an edge between those 2 points. And if 3 circles intersect, like here, we have the intersection of 3 circles right here, what we'll do is we'll create a 2 simplex there. And we can continue this on into higher dimensions. So again, the idea is from a point cloud, we have created now this simplicial complex, which is a topological space. Is this making some sense? there any questions? Please don't hesitate to ask questions.
So these would be like predictors you measured from your data set? Is that what this would, you'd initially get these points in some high dimensional space?
Can you explain a little bit more what you mean about predictors?
Well, this, I mean, you're setting this up to solve some data problem.
Yeah, so you're given the data, and assume that as long as the data are in metric space, we want to know something about the shape of what those data look like.
I guess I was assuming a predictive.
No predictors
This
yet.
sounds super.
We're not doing any statistics yet.
Okay.
We just have a point cloud, and from that point cloud, we want it to create a topological space. So this is the topological space then.
Okay, so what, some measurements were taken to get these points.
Yeah,
right?
so at the very beginning, so we have these points were, I don't know, sampled from something,
Yeah.
right? And somehow you have some distance between the points. That's it. That's the only requirement.
And you might have collected like many different measurements. So each point could be in a higher dimensional space.
Yes. Yeah. Oh, we're saying we're using measurement in different ways, but yes. So yes, these points. The whole point is that you shouldn't be able to see this. These data should be lying in a space where you can't see them.
Right.
Because if you can see them, if the data are in 2 dimensions and you want to know what the shape of the data are, what do? You look at it and say, hey, it looks like a circle to me, right? But if you can't see the data, what do you usually do? You do something like support vector machines or PCA, right, to project it down onto space. But you lose a lot of information. Like if you have million-dimensional data, you project it down onto 2 dimensions. What have you lost? So the idea here is to try to figure out what you've lost. Does that make some sense?
Yeah. So I'm curious how you define distance then. I mean, do you just normalize all your data?
It depends. It depends on what you're trying to do, really. I mean, we haven't even gotten to the statistics yet at all. So.
But before, I mean, just to pick these regions, you have to define the distance, right?
To do this?
Yeah.
Yeah, so you have data that are lying in a metric space already.
Okay.
Does that make sense? Or,
Yeah, but I mean,
I don't know how the metric
depending on
space.
the units of what you measure.
Yeah,
you measure feet versus-
somebody has already done that.
Okay.
Yeah. Yeah, that's a good question, and I think we will speak a different language often. That's okay. I have a lot to learn from you guys. So again, the idea is you have a topological space. You have a point cloud. You create a topological space from those data, given a radius r. But the question is, how do you choose what r should be? Well, if you choose r to be this radius, right? What are you going to see? Well, look, I have an interesting structure here. There's like a loop here. There's a loop here. There's loop here, right? There's something interesting happening. There are a lot of interesting things happening. But when we go back, you might, if someone, again, this is in 2 dimensions. If someone asks you, hey, what's the shape of these data? You might say, well, there's 1, 2, 3, 4, 5 loops. That's what it looks like to me. But on the other hand, what's the shape of this structure, this structure, this structure, this structure, and this structure? Well, it's another loop, right? So the answer is there isn't one right choice of r to pick. The correct answer is that, is this on the next slide? No. The correct answer is that you want to consider all possible values of r, because each value of r might give you information about the underlying structure of the data. So I want to show you, I want to give you, and actually I have, this is one thing I'll have you download, but I want to give you the idea of how persistence homology works with this, program that a couple of guys and I put together. So the idea is that you start off with a point cloud like this. And what happens is that you let your parameter increase over time. So on the right-hand side, ignore all this. What you can see to start with is that right now the radius is starting off at a value of 0. And then as the radius increases, you can see some sort of interesting topological space happening. It increases, and it ends up with this big messy stuff. And what happens is that eventually the radii get so big that there is no loop anymore at all. Okay, so if I go back to the beginning, if I can, maybe I can't. Oh, there we go. I can also do this without the circles, and you can see how the simplicial complex changes over time. So what are these things on the right denoting? And what's happening here is that dimension 0 in homology counts the number of connected components. So if I look at all these guys up here, I want you to notice, I hope you notice this ticker down here is moving to the right. So if I move all the way to the left, how many connected components do I have? Well, I have a connected component for each point. Right? I don't know how many points I have there. 1, 2, 3, 4, 5, 6. 6 times 6, about 36 maybe. But as I move to the right, some of those connected components become joined together. Does anyone know single linkage clustering? Has anyone heard of that before? No? This is single linkage clustering. It's the exact same thing. But if you haven't seen that before, that's okay. So yeah, you can see that if I want to know how many connected components do I have at this time right here, what I do is I go up to dimension 0, and I count that I have 1, 2, 3, 4, 5, 6. 6 connected components. 1, 2, 3, 4, 5, 6. 6 connected components. Okay? What does dimension 1 in homology count? Well, dimension 1 in homology counts the number of loops that I have. The number of loops that aren't trivial, that can't be collapsed to a single point. So how many loops do I have? 1, 2, 3, 4, 5. This guy's not a loop. Right? So if I come over here and I count up 1, 2, 3, 4, 5. All right, this guy right here isn't counted. 1, 2, 3, 4, 5. This guy right here will start as soon as I add an edge right there. So if I move to the right one more spot, there it is. And now I have how many loops? 1, 2, 3, 4, 5. This guy's not a loop because it can just be collapsed into nothing. So again, I have 1, 2, 3, 4, 5 loops. Does this make sense? So that was a processing demo. I want to give you a little bit more information about what these things, what this stuff on the right is. It looks like a barcode, and so we call it a barcode. That's it. So the barcode provides a summary of how homology changes as the radius, as the parameter changes. So what we do is we look for topological features that persist over a large range of R. And we conclude that if a topological feature persists over a large range of R, then that gives us information about the underlying shape of the data. So for example, if I had data that looked like this, right? If those were my data, and I created a very small radius around each one of these points, the topological space I'd end up with would look like an annulus, right? I mean, the topological space that I would have would be a circle. And that circle would last for a long time, right? I mean, the radii would get bigger and bigger and bigger, but eventually the radius here around this point would touch the radius around that point, and the circle would go away. But for a large range of R, you'd see a circle. Whereas maybe you have some error over here. Point here and a point here. Well, you'd have a circle for an instant, but then it would go away. And you conclude, oh, that's just noise. Okay? So that's what's happening in this barcode right here. If I were to look at this, just without doing any statistics at all, I would say, hey, it looks like my data, if this is in dimension 1, so this dimension 1 counts the number of cycles that I have, the number of holes that I can stick my arm through. Looks like there are 2 cycles that persist. This guy right here is in dimension 2. It looks like to me like there is one void that persists. Like maybe the data lie on some sphere, and then maybe a circle, something like that. Is this making a little bit of sense to people? So this is just, again, just back to the pipeline. So you're given a set of points x and a parameter r. What you do is you create a simplicial complex. And here's how the simplicial complex is created. If, well, the formal n-simplex, so I have an n-simplex that exists if and only if the distance between all the points in that simplex is less than r. And I just gave you this interactive JP DWB demo. That's this program right here. So I have some questions that I would like you to try to answer using this demo. Just involving simplicial complexes in 0th and 1 degree persistence homology. So are you familiar with GitHub? You use that for collaboration and stuff. So download this, the slides are in there too, so you can have them forever. And yeah, put this on your computer and try and solve some of these problems. So I'm going to go to the next slide, but I think the web page is still there. Yeah. So here are some questions that you can work on together. And if you have questions, I will help you. This and this. So what did you get for number one? Hope everyone got number one. 4. That's correct. And this, I haven't proved this at all or thought about this at all before I give this talk, but what's the minimal number of points that you need to get 3 connected components and 2 holes? Anyone have a good guess? You guys had a good guess? What was your guess? 8. Is that what you had too? So you have like this figure 8 thing, and then you have just 2 points, right? Okay, great. And then, so this is where things kind of get complicated and interesting. So what's the largest degree of homology that's possible, geometrically feasible in R2? And what did you say? What do you think it is? There's no shame. You thought it's 1, right? Probably. But I want you to think about this. Imagine that I have 8 points. 1, 2, not 8 points, 6 points, I'm sorry. Imagine you have 6 points like this. And so these are all aligned on a circle, okay? So they're all, I don't know, like opposite guys are equidistant from each other. And then if I create a radius large enough so that this point right here connects to all of the other points except for the opposite point, right? And then the same thing with this guy, it's going to connect to all the points except for the opposite point. And same with this guy, it's going to connect to all the points except for the opposite point. Same with this guy, it's going to connect to all the points except the opposite point. And this guy is going to connect to all the points, I guess I forgot one right here, right? What is the dimension of this guy? Well, this is the exact same thing as this guy right here, actually. So it's possible here to have a sphere in 2 dimensions, which is kind of crazy, right? But the thing is, so you have to get, the reason I ask this question is you have to get away from the idea of thinking that the topological complex that you're building is lying in the space, the same space where your data lie. It's not. It's a formal simplicial complex. It's lying somewhere else. So from your data, you've created a topological space, and the topological space lies somewhere else. So the size of your topological space is not restricted by the dimension in which your data lie. And this is important in theory, so it's kind of a fun question to ask most people, because intuitively this shouldn't be able to happen, but it does. So here's the answer to this question. What's the minimum number of points required to have Betty 2 equal to 1? Oh, it's right here, it's 6. Right? What's the minimum number of points to have Betty 1 equal to 1? So this is right here, was Betty 2 is equal to 1. What was the answer to number? There's 4, right? So Betty 1 equals 1, and the idea is then you just have, right, something that looks like this, right? What if I want, now you can't see this anymore in your head, right? Because it would be a 3-dimensional sphere, which is really hard to see. If I want this to happen, how many points do I need?
8.
8. And if I want Betty n to equal 1, how many points do I need? 2n plus 2. So what's happening here? How do I go from here to here? You might have heard me say this when I drew this picture right here. Well, what I do is I say, hey, this is like the equator. What am I trying to do? I'm trying to build something that looks like a sphere, like a basketball. Right? This and this are the exact same thing to me. I just kind of smooth this out a little bit. Right? So what do? I say, hey, this is like the equator of my sphere, of my Earth. And then what do? Well, okay, I have my equator like this. And then I just need to add the North Pole and the South Pole. And then I get my thing that has the exact same homology as a basketball, right? So what do I do if I want to build a 3-dimensional sphere? Well, I say this is the equator of my 3-dimensional sphere. What do I need to add? A North Pole and a South Pole. You can't see that anymore, though. But that's how it happens. It's called the suspension in homology. How much time do we have? Oh, that's it? We didn't get to anything at all. Geez, I feel like, I feel really bad. Can I just take up 3 more minutes of your time and kind of show you what's like, oh, I feel horrible. Well, I hope you learned something about, because we didn't even get to the statistics. We like drew some funny pictures and that's it. So again, what we're trying to do is we're trying to get to these barcodes. And what these barcodes are telling you, they're telling you the dimension of your vector space at every radius. So at this radius right here, I know the dimension of my vector space for the first homology group is 1, 2. I have 2 generators for that homology group. That's what the Betty number is telling you, is how many basis elements do you need in your vector space. So let's suppose that I have a set of data that look like this, okay? And if I set r equal to 0, if you just look at this, it looks like you have 2 clouds of data, right? Well, how can we translate that into the language of homology? Well, what we can do is we can say, okay, around every point we're going to create a circle of radius r, we're going to let that radius grow, and we're going to look at the graph, the resulting graph, and then the resulting graph is going to define a simplicial complex for us. So, and if we have a topological property like a Betty number that persists over a large range of r, we're going to say, hey, that tells us something about the data. So what would we expect here is we'd expect to see 2 connected components last a long time, because eventually, as the radius grows, all of these points are going to get connected, and all of these points are going to be connected, and because there's some distance between the points here, I'm going to expect that those 2 connected components, those 2 graphs will persist for a long time. So what I'm going to end up with something that looks like this for a large range of r. And then eventually, these 2 are going to get connected also, but for a large range of r, I'm going to have this graph, and that's going to tell me, hey, I think I have 2 clusters in my data. Again, I told you before, this is the exact same thing as single linkage clustering. The point is that you want to do this in data, in higher dimensional data. Oh, man. So there's a nice program called Ripser. Boy, I don't know. I don't want to take any more of your time. I hope you learned something with me. It's 4 o'clock. Can we do 1 example in Ripser at least?
Yeah.
So you downloaded all, if you look at the file that you downloaded, you have 2 folders. Well, you have the slides, you have this 1 folder, JPDWB, and then you have another data set that's just called clouds, I think. Is that right? Can anyone tell me? Okay. So if I, a tool for computing persistence homology barcodes. So if you just have a spreadsheet of data, you can't see what it looks like, you can't plot it, and I want to know what does topology tell me at all, you can go to www.liveripser.org or just liveripser.org. And what you can do is you can say, hey, I'm interested in inputting a point cloud. So you can click on point cloud right here. And then I'm interested in computing the dimensions. So this is from dimension 0 to dimension 2. Again, it's telling you Betty 0, Betty 1, Betty 2. That's it. But you can do it in higher dimensions. It just might take a little while. But you can do stuff in dimensions that you can't see. And then you're going to choose a file. And I don't remember where I put this. Probably in presentations. Here we go. Data. I guess I call the folder data. And then you can input, so that first data set that we looked at was cloud 1. And we can see, and I should have picked a smaller size, like up to distance 2. Oops. Oh no. Sorry. Presentations, labs, data. There we go. What do we see here? This is just in dimension 0. What do we see? We see 2 bars that persist over a large range of r. Now, 1 bar is going to persist forever, because there's always going to be 1 connected component, right? But we see that there are 2 bars that persist. That tells me, that suggests to me that there are 2 connected components in my data. And if I scroll down here far enough, what is all this stuff right here? Well, as your graph is being formed, right, some cycles are going to be formed, and they might go away really quickly. That's what's happening here, is that a lot of these bars, these are all just noise, cycles being created and destroyed right away. That's what's happening. And then nothing happens in dimension 2. I don't know. That's the end of the talk. I spent all this time creating these data sets for you to try and getting real data that give you nice shapes. One project I did with, I kind of liked, I did with an undergraduate student. where we looked, do you guys know anything about like atoms,
Adam.
like chemistry? So I didn't know this, I didn't know anything, but so if you look at a hydrogen atom, right, you look at where the electron sits, right? Well, the electron gets closer to the nucleus, far away from the nucleus, and it keeps kind of I mean, you draw like this picture where you have the nucleus and then like a circle around it. It's not how the electron behaves at all, right? Well, it turns out that if you remember like your periodic table, every time you go down one level in the periodic table, that's another electron shell. So if you look at the second electron shell, those electrons don't get close to the nucleus if they stay in the third shell. Well, so what is that going to look like then? Well, it's going to look something like, so if I project it into 2 dimensions, here's the nucleus, right? And I have one shell around like this, and I have another shell that goes around like this, and I'm going to have a bunch of points in here. So what do you expect the homology will be? Now this is happening in 3rd dimensions, I kind of drew it in 2 dimensions, but you're going to see a void in the middle of that guy, and that's one of the examples that I put on here. It's data 6, if you're interested in looking at that. So what will you see? You'll see one connected component. Let's just put it in here and see if we can get it to work. Takes a while. Data 6. I don't really remember what. Just quickly. Yeah, to distance 2. So let's see. So this is all just noise, and it's still taking some time. But eventually it will pop up down here and it will say, hey, something's happening in dimension 2 because there's a void there. And I guess, I don't know, that's really is the end of the talk now. And we can sit here, I don't want to make you sit here and wait. But thank you for coming and listening.